All right, so this is the fourth day of the class. If you want a quick, review of what we did last time, and to make sure you kind of understand it, you might want to look at the board from what the previous instructor wrote from an hour ago. But here he's talking about solving a system of linear equations and how you take your system, you write a matrix, you put it in reduced row echelon form, and then from that you can read off the solutions to the system of linear equations. So hopefully that should look familiar to you from last time. All right, so what we're going to talk about today is more about matrix algebra. So some algebraic properties of matrices. For example, we'll talk about the distributive property, the associative property, the commutative property, and so on a little bit. And the surprise with matrix multiplication is it doesn't commute. A times B need not equal B times A. We'll also talk about symmetric matrices, some, which we haven't quite touched on yet, but they come up in the context of transposes of matrices. So I'll put a little box here for the things we're going to talk about. So matrix algebra. You consider the collection of all matrices and try to do arithmetic and algebra with them. What sort of properties do you have? I'll just write transpose, so further properties of transpose. And then coming up, we'll be talking about inverses of matrices on Wednesday, but we probably won't get anywhere with them today. So this is our to-do list for today. Just some quick reminders as I look at my notes. I have office hours tomorrow at noon in my office. You can come by and talk to me then. Also, as always, you can talk to me for a few minutes after class, because all I do from now until an hour after the class ends is eat lunch in the hub and then teach another class. So, another reminder, the first homework assignment is due Wednesday, which, as I hope you know, means you simply have to send an email to the address that's given there saying, I did the homework. That's it. There will be another homework that will be assigned on Wednesday using WebAssign this time. Okay? I've also chosen what seem to be basically the canonical midterm dates, so you'll want to mark these in your calendar. They are April 24th and May 15th. These are both Wednesdays, so they're the day after an office hours day. They're roughly a third and then 2/3 through the quarter. Okay? So make sure that you definitely mark your calendar with these two dates. I've also added them to the syllabus and so on the website, so you can find them online. But you certainly want to be here on April 24th with a pencil so that you can take an exam. And likewise for May 15th, because it would be very bad for your grade if you didn't take the exam. And plus, it would be really exciting if your heart pounds and you take an exam and you have to be really fast and know things. Okay, I took a screencast, that is, I record all the audio and what happens on the screen, and I posted it to YouTube for the lecture last week, and I just started that thing running now. So each day, if I seem like I might forget, feel free to remind me to make that. Yes? So what I did was I went to the 308 website, and right on the very front page of that, where it says the README file, there's now a link to the YouTube video. Okay? And I only added that about an hour and a half ago. The thing was, right after this, I taught the other class and went home, and I had slow internet, and I didn't want to upload the video because it was huge, so I uploaded it this morning. So, in any case, that's there. So it's a way that you can get the audio if you want to review things or something didn't make sense. Okay? And as long as I don't forget, I will continue to do that throughout the quarter. And as long as one person here reminds me every day, I won't forget. It's pretty easy to do. Okay, that's it. And that's the website. But you can always go to wstein.org, and then there's a link to the 308 webpage. Okay, before we get going, any questions? All right, so we're going to talk about algebraic properties of matrices first. So there's some really easy ones. You have two matrices for which the sum makes sense. It's pretty obvious that A plus B is the same as B plus A, because you add component-wise. Okay, that's just completely easy. Another fact, which is slightly less obvious but still pretty easy, is that A times B plus C is A times B plus A times C. So that's just a fact called the distributive property of matrix multiplication. So it's useful and it's natural, and you're of course used to it because you have exactly the same thing with normal numbers. And here, in order to see that this is true, you kind of just think about what the definition is, but I'll give you a way of thinking about matrix multiplication that will allow us to reduce this to a special case, which will make it easier to believe. So here's an observation that I often find very handy about what matrix multiplication really is. So if you take a matrix A, multiply it by a matrix B, and you view B as a bunch of columns, as a bunch of, say, column vectors, if you like, then you can think of this as A times, and this notation I'm writing right now is kind of like what it's like in my mind. I think of B as a collection of columns all put together in a matrix. I'll just say that there are n of them for now. Okay, does that make sense? This is a notation that I'm just making up. Each of these is a column. Column, okay. And now you can apply A to a single column, and you'll get, what I mean by this is just the product of, so if you take a matrix and apply it to a matrix with exactly one column, how many columns does the resulting matrix have? You just think about the definition of multiplying. So it's just so you can see this with actual concrete numbers. Lots of abstract. It might be a pain to do the arithmetic to multiply these, but if you did it, you have a number right there. You have a number right here and a number right here. So when you take a matrix that has exactly one column and you multiply it on the left by a matrix for which that makes sense, you end up with something with exactly one column. If you think of matrices with one column as vectors, kind of the same thing, then you can think of this as the matrix doing something to the vector, by the way. So here, what I mean by A times B1 is you take the first column of the matrix, view that as a matrix with one column, and then multiply these two things. The result is, again, a column. So this is a column. Now, the next one, A times B2, A times Bn. Okay. It turns out that this matrix I just wrote down, whose columns are the result of applying the matrix A, of multiplying the matrix A on the left times each of the columns that are given, that's exactly the product A times B. These are equal. And that just follows from the definition. Think about what would happen if we were to take, let's say this matrix is A. If you multiply by a matrix with multiple columns, what happens? Well, you take this matrix A and you do this dot product thing 3 times, and you get the first column. And then you look at the second column and you do the same thing 3 times and you get the second column. So what happens in each column is completely separate. So you can think of, in your head, anytime you're multiplying two matrices, it's absolutely exactly the same as taking the matrix on the left and applying it to each of the column vectors in the matrix on the right, and then looking at the resulting matrix. Okay? That's what it is. Just for fun, let's do a really quick little 2x2 example so that it won't tax our arithmetic too much. Okay, we're going to multiply these 2x2 matrices. Let's think of it, as we do the process, of multiplying them, instead of just using some formula, let's think of it as taking this matrix and multiplying by the first column, and then this matrix and multiplying by the second column. Okay? Just for fun, let's do it that way. So what we do is we take this matrix times this first column, and that's going to give us the first column. So 1 times 1 plus 2 times 4, that's 9. 3 plus 16, that's 19. And then we take this matrix and apply it to the second column. So that's 5, and then 15. Okay? So it's exactly the same as what we did before. I'm just emphasizing that conceptually you can think of multiplying one matrix but another as you take that matrix and apply it to each of the columns. Any questions at all about that? And it also makes it a lot easier to remember the definition of matrix multiplication. So what does that have to do with this? Well, if we view B and C as having one column, then it's just a lot easier to think about this. And you could then, because when you add together matrices, it's also like just adding together the corresponding columns. You can easily reduce to that. So just point out a similar thing: A plus B. This is given by columns A1 through AN, and B1 through Bn. Then the sum is you just add together the corresponding columns. So the point is just that for matrix multiplication and addition, you can think of matrices as kind of like just a list of columns. And then operations work on each of those columns. So that's conceptually, I don't know, often it's amazingly helpful. So then, looking at this specific identity, if you imagine A times, let's just write this a column vector plus another column vector. So, I don't know, that notation looks a little funny, but I'll just write it. A matrix with one column plus another matrix with one column. Okay, so by this I just mean matrices with one column. So if you do this, what happens is you can, what happens here is, let's say the top entries are B and C, and there's other entries. If you add together these two vectors, or matrices with one column, the top entry will be B plus C times A, and so on for the other entries. And so when you multiply A by the sum, you get each of the rows dotted with this column where the entries in the column are the sum. So for example, the first entry of A is 0, or sorry, if it's A, then the very first entry of the result will be A times B plus C. And similarly, if you do it in the other order, if you first multiply the matrix A by this column, then the top left entry will be A times B. When you sum up, I should write out. It's too confusing not just writing out lots of notation, unfortunately. Okay, so I'm just going to write this out so it's a little bit easier to read. So let's say the entries of A are Aij. This notation means that you have this matrix A, and the ij entry is A sub ij. That's the notation we're going to use for it. And then for this matrix B right here, say its entries are Bij. And if it only has one column, that means that j is always 1. And likewise, let's say the entries of C are Cij. So if you compute A times B plus C, what we'll do is we'll just write down a formula for a generic entry of A times B plus C, and then we'll do the same thing for a generic entry of A times B plus A times C. And you just see that via simple manipulation you get from one formula to the other. Therefore, they must be equal. This isn't a particularly difficult thing, but I'm going to show you the proof just kind of writing everything out so you can see how that works, because you have to do that in some cases that are more difficult, and seeing things in a case that isn't too difficult, but using the method that generalizes is a good idea. Okay, so let's just write out a little formula for A times B plus C. As a reminder, first, when you multiply two matrices together, A times B, you get some matrix, and the ij entry of this matrix is equal to, so if you have a matrix and you put some subscript like this, that means that entry of the matrix. So that's the I, jth entry of the matrix A times B. It's A I1 B1J plus AI2 B2J plus dot 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 plus AI. So here you have to worry about how many rows A has, or actually how many columns A has and how many rows B has. So let's say that A is an n by m matrix and B is an m by r matrix. So this sum goes up to m. So that is the ij entry of the product. Let me convince you that that's the same as what we've been doing already. So this is a scary looking formula with lots of subscripts, but all it is the following. If A has these entries aij, that means the first, so the ith row is ai1 through aim. So this is the ith row that I've written. And then the matrix B, its jth column has entries B1J all the way down through B sub MJ. And remember, the way that you get the ij entry of the product is you take the ith row and you dot it with the jth column. That's what we've been kind of doing over and over again in various contexts. And what do you get here? What this formula I've written down is just literally taking the ith row, taking the entries there, and then multiplying them by the corresponding entries in the column over there. And that's the formula you get. I mean, it's just AI1 times B1J, AI2 times B2J, etc. So this is a kind of algebraic or formulaic way of writing down the definition of matrix multiplication right here. Let's see. I found that in proving lots of stuff and understanding linear algebra, knowing this formula, like just like that, was often extraordinarily helpful. And you really want to know it kind of backwards and forwards. All it is just an algebraic way of writing down, dotting those two, dotting a row times a column. Yes? Where? Right here?
Yeah.
Okay, so I wrote n times m, make that bigger, meaning that A has n rows and m columns, and B has m rows and r columns. The way it works in terms of these, the number of rows and columns is that you can multiply two matrices if the number of columns of the first one matches the number of rows of the second one. So when you stick the matrices next to each other, if the two numbers in their dimensions, that is number of rows and columns, are the same, these two are the same, then you can multiply them. If they aren't the same, then you can't. I'll just record that up here. You can multiply an n by m matrix times an m by r matrix. And that's the only thing you can multiply. So if you just choose any numbers at all for n, m, and r, then you can do the multiplication. It's just kind of like, if you were to actually write down for specific values of n, m, and r, the matrices and then try to multiply them, and by here I mean multiply, I should emphasize the order in which this multiplication is happening. So by this I mean A times B, where A is n by m, and and B is M by R. So that's the only time you can multiply. Why? Because this has M columns, so when you try to dot a column of A by a row of B, the M's match up. You have exactly the right number to do the multiplication. So if you ever forgot this, then you could just consider two kind of big matrices with random NM, random dimensions, and figure out what relationship would you have to have between the dimensions so that you can multiply them. Nonetheless, again, this is a super useful thing to just memorize, that these two numbers have to be the same. It's really natural, right? You're going to multiply two things together. It's nice if the numbers in the dimensions of the two objects, it's really nice that the rule is that they're exactly the same. Those two numbers that are next to each other have to be equal. All right, I'm going to stop for 15 seconds to see if anybody asks a question. All right, I'm going to stop until somebody asks a question. The lecture will not go on unless somebody asks a question. It can be really dumb, but something. Yes?
So that's basically like saying the matrix on the left, or that matrix's number of columns needs to match the one on the right number.
Exactly right. That was 100% perfectly correct. Yes, that's exactly what I'm saying. The number of columns of the matrix on the left has to be the number of rows of the matrix on the right in order to multiply them. And in terms of this formula, you wouldn't be able to kind of write this down because you'd be missing entries. If you were writing this and the number of rows and columns didn't quite match up right, and you're using C, you would get a segmentation fault. Or it'd be a buffer overflow. Somebody would hack into your matrix. And by the way, you can also write it like this: A sub I k U sub kj sum k equals 1. So these are just equivalent ways to write these two things. And again, what I'm writing here is just the algebraic way of saying you take that row and you multiply by that column. That's what I'm writing here. Because this is a dot product, right? So you sum up the product of the corresponding entries of two lists of numbers. Okay, so that's what the product of two matrices is in terms of a formula. And now in order to check this statement, this amazing claim that A times B plus C is A times B plus A times C, we just write down, in terms of a formula, what both sides of this claim are. Okay? So I'm just going to unwind. I'm going to write a formula for the ij entry on the left side and the ij entry on the right side. And if the two formulas match up, then we're good. And of course they will, unless I made a mistake, in which case we'll fix it. Okay, so on this side, let's write down the ij entry of this product. So by that I mean, take A times B plus C. We're just going to write down the ij entry. So we just use this formula. So the sum, k goes from 1 to m, of aik times, and now I have to give the kj entry of the matrix on the right. The kj entry of B plus C is B sub kj plus C sub kj. Okay? Seem reasonable? Annoyingly algebraic, but still it's fine. And now, on the other hand, that's all we're going to, it's really a pretty simple calculation. I wrote down a formula, just unwinding the definitions more algebraically, for the ij entry of A times B plus C. Now let's do the same thing for the ij entry of A times B plus A times C. Are you having trouble seeing over my laptop screen? Okay. So writing down a formula for the ij entry over here, well, we just have to find the ij entry of A times B, and then add that to the ij entry of A times C. So what is the ij entry of A times B? It's the sum aik, akj, k going from 1 to m. That's the ij entry, oops, that's wrong. That's the ij entry of A times B. So this is A, B, and you take the ij entry. That's what it's equal to. And now we'll add to that the ij entry, A equals 1 to m of A, I, K, C, K, J. This is the ij entry of A times C. I've just written down the ij entries of these two matrices, and when you add them together, the ij entry of the result is the sum of the I, comma j entries of each of the matrices. Yes? Yeah, because we're writing B plus C, this only makes sense if B and C have exactly the same number of rows and the same number of columns. Yes. Okay, any other questions? All right, and the big question is, are these two expressions equal? Yes, because all you have to do is use the distributive law for normal numbers. These are just standard numbers. We're assuming our matrix has entries that are, let's say, real numbers or complex numbers or something. And then you can just rewrite this like that. In other words, you combine together, since it's a finite sum, you can reverse the order, or you can just combine this into one big sum, and you end up with the same thing you have over here. Well, this expression right here, this is AIKBKJ plus AIKCKJ. And so you get 2m total summons that look like this. And over here you have 2m total summons, and they're exactly the same. And so these two are equal. So that's the write it all out in terms of numbers reason why A times, or not in terms of numbers, but in terms of algebraic formulas, that's why A times B plus A times C is the same as A times B plus C. There are a lot of identities algebraically involving matrices that you can verify in this manner. I don't find this, this just, hopefully if you follow the lines of reasoning here, this convinces you that it's true, but doesn't give you any real feeling for why it's true, or understanding of it at all, or feeling for it. So that will come later. And personally, I like to think about it as just the special case when B and C are each one column, and then you're just taking a matrix times the sum of two columns and saying that's the same as the matrix times one column plus the matrix times the other, which if you just imagine doing the multiplication is really pretty obvious. All right, so that's one fact. Now here's a harder one. A times B times C is the same thing as A times B times C. In other words, you can move where the parentheses are. This is called associative. I can erase this. And I'll just write kind of to remember, since probably the most important thing we did so far is that the ij entry of the product of two matrices is the sum of AIK BKJ. So this one formula allows you to deduce many things. Okay, so the next statement is that the associative law holds. This is actually, so there are some cases, for example, if this is a 1-by-1 matrix, where it's really easy to see this, but in general it's kind of tricky. This is hard to verify directly. By verify directly, for example, you could just start writing things out and try to write out a formula for the ij entry of this product of three matrices. And that would, in theory, work, but it just might get very tedious as far as all the numbers that are involved. and seeing that they're equal. Oh, that's not too bad, but is it that? Maybe it's really easy. I don't know. Here's the thing. So maybe it is actually fairly easy, but here's the thing. If you do that, it doesn't give you any reason why this should be true. It's just that you know that it's true at the end. And who wants that? So instead of instead of convincing you that this is true via a calculation like this, which probably wouldn't convince you anyways, I will explain to you why this is true via a conceptual idea instead. I'm going to write slightly hard. It's not that hard, but maybe let's just say it's hard to get anything out of verifying directly. I mean, in some soul-searching sense. So instead, here's a conceptual reason. Just for fun first, here's a random example. I just took 3 matrices, totally at random, that are 4 by 4, and I multiplied it in both ways, A times B times C and A times B times C. And you can see that the results came out the same. All right, so now the reason for associativity. I won't consider this really a formal proof, but here is a good reason. So if you have a matrix A, this is let's just, for simplicity, let's just say it's an n by n matrix. So I'm assuming it's square, but this isn't at all essential to anything. Then we can imagine this matrix as giving us a function that takes as input a column vector with n entries in it, and then gives us back a column vector with n entries in it. Okay, let's think of it as a function. Think of A as a function. Of A as giving a function. And the function is just given a column vector B, or a matrix with one column, B. B gets mapped to A times B. So this is a function, and it takes any column vector and gives you back another column vector. So if you imagine the kind of space of all column vectors, of all vectors with n entries, then you can take your matrix. Given any vector with n entries, you can apply the matrix, and you get back another vector with n entries. Okay? For example, n could be 3. And then what this would say would be, given any point in 3 space, and a fixed choice of matrix, you get another point in 3 space. So in other words, matrices define a way of taking all the points in 3-dimensional space and transforming them somewhere else. Maybe rescaling them all, or rotating them around, or something like that. So just to make this concrete, we take my favorite 2 by 2 matrix, 1, 2, 3, 4. That's A. Given any vector with 2 entries in it, we can get back another vector with 2 entries in it. So let's say our vector is, which I'll draw geometrically. I'll say it's 1, 2. So you can think of that as the x-coordinate is 1 and the y-coordinate is 2. So if you apply this matrix, you get back another point. What point do you get? Okay, I heard the first coordinate, 5. And what's the second coordinate of the result? 11. So that's over here, and then what, right about there. Actually, 1, 2, 3, it's right here. So what happened was this point got sent to that point. That's pretty neat. So given any matrix at all that's square for now, you get a transformation of n-dimensional space naturally associated to that matrix. So for a 2 by 2 matrix, there's some way of taking every point here and transforming it, given by this matrix. For example, if you were to take a picture and draw it right here, you could then apply left multiplication by this matrix to that picture, and you get some weird distorted version of the picture out if you moved all of the points as given by this matrix. Now you can start wondering, what kind of transformations do you get? What do they do? Maybe do they all just rotate stuff around? No, not just rotation, because look, this point that's really close got moved really far away. So the sorts of things that might happen when you apply a matrix is you can rotate, you can scale, you can kind of shear things. You can also have something like, say, the 0 matrix, which takes every single point and sends it to 0. And that just collapses everything to a point. You can also have matrices that take the entire plane and collapse everything to a line that goes through the origin. So there are lots of different possibilities. Okay, so what's this have to do with the associative law? Well, matrices are the same thing as functions, or at least they give you functions, and matrix multiplication corresponds to function composition. If you have two matrices, say A and B, and then some vector x, doing so, actually, at this point, I think it'll be best just to write the sentence. Multiplying matrices, and then we have to just check this at some point. Multiplying matrices corresponds to composing functions. So if you have two matrices, and you consider the functions that they define over here, you could take the two matrices and multiply them, and you get a third matrix, and that defines some function. It turns out that that function is just the composition of the first two functions, the functions corresponding to the first two matrices. So with this dictionary, the assertion that you have the associative law, that's the same as the fact that function composition is associative. So if you have functions and you do f composed with g composed with h, it doesn't matter in what order you do that. This is the same as f composed with g composed with h applied to something. This is something you probably know from calculus or pre-calculus or something. Because what is this? What does f composed with g composed with h of x mean? It means you plug x into h, and then you plug that into g, and then you plug that into f. And it's just exactly the same thing. It doesn't matter if you think of it as f of, they're all just f of g of h of x. So function composition is associative. Matrix multiplication is the same as function composition. And there's a correspondence between matrices and functions, which in fact will be a big part of the subject of this course. Is given a system of linear equations, there's a corresponding matrix. Associated to that matrix, there's a function, which is called a linear transformation. And you study these linear transformations a huge amount in this course. There's various objects associated to linear transformations, like kernels and cokernels and so on. Okay, so the quick summary, though, of the reason for associativity is that matrices correspond to functions, and associativity is very easy to see for functions. Okay? That's a conceptual reason. Matrices correspond to functions. Functions compose nicely. There are other contexts in math where you have objects where you have associativity, but it can be incredibly difficult to prove that associativity works. For example, in public key cryptography, the by far best approach to doing public key cryptography is to use something called elliptic curves. And there, the arithmetic that is happening all the time when you're like using your cell phone and things are being encrypted, that involves something that is associative, but the proof is quite difficult, believe it or not. Okay, the next thing, before we go on though, any questions? So in our summary box here, just put A times B C equals A times B times C, because matrices are functions. Okay, the next thing is matrices don't commute. If you multiply A times B, you might not get the same thing as B times A. Okay, the challenge right now is to come up with the simplest example we can that illustrates this. A times B need not equal B times A. How can we find two matrices that illustrate this claim that I'm making? Well, let's actually just assume that they're both square matrices for simplicity, so that it makes sense to multiply them in either order. Because you're right, that would be a big problem. If it didn't make sense to multiply them in one of the two orders, then you would have on the left something that makes sense, and on the right it doesn't even make sense. And so then they can't be equal. But let's just say that they're square. And being systematic, there's no way you're going to do this with one-by-one matrices. Because they do commute if they're one-by-one matrices. So any ideas? Yes?
You do like 1, 0, 0, 0.
Okay. Here's the proposed matrix.
And then 0, 1, 0.
0, 1, 0, 0. All right, he's simply pulled this matrix out of thin air, and then another one out of thin air, I guess. Or maybe he checked it. Let's just multiply them and see what happens. And then compare it to doing it in the other order. So what do we get here? We get, I guess, 0, 1, 0, 0. And on the other hand, multiplying the other order, we get 0, 0. Oh, it's already failing. 0, 0. Great. This statement fails so, equality of A times B and B times A fails so miserably that almost any random choice of matrices A and B, for which it even makes sense to multiply them, will be an example that illustrates the failure of this. So I'll just emphasize that the commutativity fails miserably. A times B very, 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 very much fails to equal B times A. Extremely hard to ever have A times B equal to B times A. Very rare. Nonetheless, if I take any n by n matrix A, can you think of an n by n matrix B that will definitely commute with A? That is, for which A times B will equal B times A. What?
I mean, it could be like anything that
Wait,
has.
don't you just answer? What?
Yeah, like a matrix full of all together.
It might work. If they're all 0, it would definitely work. If they're all the same, that's a good question. I don't know. Let's see. So let's say B has all same entries. Does it necessarily follow that A times B is B times A? How can we answer his question? What's your name again? How can we answer Abraham's question? His question is, if you take some completely random matrix A and a matrix B whose entries are all the same, the question is, does A times B necessarily equal B times A? One special case of this is when they're all 0, and then both sides are 0. So that's one case that's true. And you're...
Is it just saying, isn't that basically saying A times A is equal to B times A?
Why? Well, That would certainly, that's a good example. That's a different answer to the question I asked before. Given so the question I'd asked before was, given a matrix A, can you find some other matrix that definitely commutes with it? And I think you just gave a great answer to that question. Namely, take the matrix A again. A will commute with itself, because A times A is equal to A times A. So I like that. You just kind of imagine that that B is equal to A, then in fact that commutes. So great answer. But that doesn't answer his question, because he's making one of the matrices be something like this, and the other matrix is, let's say, all ones. Okay? I see many a hand, and you're next. So, are you saying that you're trying to interpret what this is, multiplying by this matrix?
Like
Yep.
matrix A times matrix B with the same entry is like times with the scalar.
Okay, that's a really good question. Let's see if that works here. So this one I get 3, 3, 7, 7. Okay, that's definitely not like multiplying by a scalar. There are matrices though called scalar matrices. Namely, you take a matrix that's diagonal, remember diagonal matrices, and you make all the diagonal entries the same. Then that is like multiplying by a scalar. So that might be useful, since you were thinking about doing that. If you take a matrix D has zeros everywhere except down the diagonal when they're all the same, then that matrix is called a scalar matrix. And it does turn out that if you take this matrix and multiply it by a matrix A, you get exactly the same thing as multiplying each of the entries of A by the number D. Does that particular choice commute with A? Yeah, it definitely commutes with A, because it doesn't matter in which order you do it. If you do it in the other order, you also get D times A. So either way, that one works. But that doesn't answer his question. Abre's question, which was, does this commute with everything? Does anyone know? Yes?
I don't think it does, because if you did it like this way, you're sort of adding up like, I mean, just because it's one, you're sort of adding up like
The columns.
the columns, and then, or the rows, and then if you were to reverse them, then you'd be adding up the columns.
That's a very good point. Here, when you do this, you're adding the corresponding entries in the columns. Whereas if you were to do it in the other order, you're doing something involving the rows. So maybe it just doesn't work. So let's just try it out. I mean, we can just do it in the other order in this case. So 1, 1, 1, 1, 1, 2, 3, 4 equals 4, 6. It's not looking good. 4, 6. Are these two matrices equal? Nope. So you can imagine, I mean, this could be a good sort of problem that you'd see on the test. If you have a matrix whose entries are all the same, and another matrix, is it necessarily the case that A times B equals B times A? That's the sort of question you might see on the test. And you can see it's not just a problem of compute the reduced row echelon form quickly, and it's not a problem for your calculator either. But it is a problem that you can solve just by using a little imagination, like we just did, and just trying it on any example at all. I mean, a big part of the problem for us answering his question was just come up with an example that illustrates what he's asking, and then you just check it. And the very first, usually in linear algebra, you're kind of lucky because almost any question at all, if you try a random example, it'll tell you what the answer probably is. That's not the case in certain other areas of mathematics. There's an area of math called analytic number theory, where usually when you compute, it dramatically misleads you compared to what's really true. Okay, so we'll start with whatever's next, which I think is mainly going to be inverses of matrices on Wednesday. Yes?
Multiplying by the transpose of the inverse of that.
Oh, that's a really good idea, multiplying by the transpose. And that does commute. In fact, that's what we'll do next. And we'll prove a formula
What about
about
the
that.
inverse?
Yeah, because then yep, that would work as well. It'll give you the identity matrix, either way. So that's, yeah, those are excellent. Both of those work. You have a question?
I just wanted to clarify. I wrote echelon.
Yes, echelon.
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 Okay. My understanding is that it's the same thing as an upper triangular matrix. Is that?
I don't think so.
No.
I think you can write down an upper triangular matrix that's not in row echelon. Yeah, definitely. So, like you could do this. That matrix is not in row echelon form, but it is upper triangular. You flip these two rows, then it's in row echelon form. The problem is that the leading one in the first row is to the right of the leading one in the next row. So that's one of the conditions in row echelon. So if a matrix is in row echelon form, then it will definitely be upper triangular. So you have one direction. But the other direction, if it's upper triangular, then it doesn't have to be row echelon form. Because part of the definition of row echelon form is that you look at each row, look at the first non-zero entry in that row, and that has to be to the left of everything else, of everything below it.
That's me to the left.
Yeah, and so this one is way over there to the right, so it fails in row echelon form.
So
I mean, it's just the definition.
Okay, cool.
So that's a great idea for a test problem, which you will get right.
And one more thing. Someone asked the square 3 by 2.